So we'll ask our first speaker to come up, Jean Kurtz from the University of New Mexico. And her topic is titled Effects of Reactive Oxygen Species on the Physical Properties of Polypropylene Surgical Mesh at Various Concentrations, a Model for Inflammation Reaction as a Cause for Mesh Embrittlement and Failure.
Hello, my name is Jean Kurtz. I'm from the University of New Mexico. This project was a collaboration between the University of New Mexico Department of Mechanical Engineering and the University of New Mexico Hospital Department of General Surgery. How do I click to go on to the next slide? Sorry.
Sometimes there's a, see this, you just click that.
Awesome.
Yeah.
This group has nothing to disclose. All the materials that we used in this experiment were donated by Ethicon. A little bit of background on polypropylene meshes. These have been known to change physical property inside the human body. They become more brittle, they shrink, and these effects have ultimately been linked to surgical complications, including eroding into tissue beds, causing pain. These changes have been noted to be more prevalent clinically in patients that have inflammatory conditions. And also, the theory behind this is that free radicals from reactive oxygen species released by neutrophils, for example, hydrogen peroxide, are causing these changes. The free radicals can attack the terminal carbon of a polypropylene, which leads to depolymerization, cross-linking of the change, and ultimately degeneration of the material. So the hypothesis for this experiment was to test this in a laboratory setting. So what we did is we obtained polypropylene surgical meshes. We exposed them to hydrogen peroxide solutions at various concentrations for 6 months. Those concentrations were 1 molar, 0.1 molar, and 1 millimolar. And we tested their change in tensile strength using load displacement testing. And we did scanning electron microscopy to look at the surface of this material for changes. Our ultimate goal was to show that at a physiological concentration of reactive oxygen species, that's approximately 1 millimolar, we would observe changes that were significant in tensile strength. So the experiment consisted of taking Ethicon Ultra Pro meshes, cutting them into identical dog bone shapes by hand. There's a diagram of the size of our samples, and exposing them to different concentrations of hydrogen peroxide solution for 6 months. These were stored in a cool, dark place. The samples were subjected to load displacement tensile testing after 6 months, and they were compared to fresh, out of the package meshes of the same brand in the same dog bone shape. We call those 0 molar because they've never been exposed to hydrogen peroxide. After load displacement tensile testing, these samples were examined using scanning electron microscopy. And specifically, we were looking at the fracture surfaces. That's where the material snaps to see inside the fibers. Here's a picture of our apparatus. It consists of 2 metal clamps with the dog bone mesh specimen in the middle. This apparatus measures tension, so it can measure the load that's placed on the material. And it also measures elongation, or the displacement, the amount of stretch the material has before it ultimately fails. So our results were all determined with 95% confidence interval. The graph you see before you is the average of the different concentrations. What you see on the x-axis is the displacement, or the elongation, and what you see on the y-axis is the load. So what you can observe if you look at the blue line, that's the regular fresh out of package mesh samples. You'll see that they're quite strong. They typically were failing at a load around something like 27.5 pound-feet. They're also significantly stretchy, considering these were 3.5-inch samples in the middle to begin with. They'll stretch over 2.5 inches before they actually snap. If you look at the yellow curve, that's the 1 molar group. Those meshes were very rigid, so they had almost no stretch before they broke, but you'll notice that the tension they were able to tolerate before they broke was significantly lower. It's around 21 pound-feet, so this is a significant change. What we found to be very interesting is if you'll look at the gray curve and the orange curve. The gray curve is our physiological concentration, that's the 1 millimolar, and the orange is the 0.1. But these are actually still stretching a fair amount, but you'll notice that the tension, the load of failure is still significantly lower than the fresh meshes. This was around 17 and a half pound-feet for the physiological concentration meshes. And the reason that they're on either side of that blue curve in displacement is because we think they're taking on a more quasi-crystalline property, as was hypothesized. So yellow is a very rigid material, and then we have a quasi-crystalline material that's not as strong. So here are the results from our scanning electron microscopy. This is a picture of fresh out of the package mesh that was never exposed to hydrogen peroxide. You'll see that it has a blunted fracture surface. These are the actual ends where the mesh was stretched apart. So if you imagine pulling apart like a piece of chewing gum, you'll see a nice rounded edge. This is very common in non-brittle materials. If you'll look at the scanning electron microscopy now of our 1 molar meshes, you'll see something that's very sharp and very angular. If you imagine pulling apart a piece of ceramic or pottery, you're going to get those very sharp edges. So this is behaving definitely like a brittle material. So our conclusion was that after a 6 months period, which is relatively not a very long period of time, at a physiological concentration of 1 millimolar, we did observe a change in tensile strength of polypropylene mesh that was decreased by 31% compared to out of the package mesh. We also noticed this nonlinear behavior, so that the concentration didn't correspond linearly to the amount of change in tensile strength. And we think this is because it's taking on this quasi-crystalline property. Fracture surfaces observed in scanning electron microscopy were consistent with this idea that the meshes are embrittling. So future research projects for this group include examining other types of mesh with different characteristic qualities like pore size, fiber thickness, and weaves, and also examining the effective length of exposure of reactive oxygen species on physical properties. I would like to thank my advisors, my colleagues, and our Ethicon representatives that donated the materials to make this possible. And thank you for having me here today to talk. Any questions?
I had a question about the fact that the strength decreased in 31% to 31%. Was that constant? You didn't mention anything about going on further as to whether in another 6 months would have decreased more. Is this a continuous process, or has it become stable at 6 months? Why did you choose 6 months?
We chose 6 months because we were really just hoping to have an effect. And this is an excellent question. This is something that I would like to know the answer to, too. Maybe it happens at 6 weeks. So that's something we should further investigate. 6 months we chose arbitrarily because a lot of the literature suggested explanting meshes around to that time because the patients would complain or have complications that time or further out.
I have a question for you. It looks like you saw embrittlement at supraphysiological levels, 100 times of what would be reality and in vivo, and what do you think are the clinical implications?
So the inflammatory process is completely nonlinear. If you were looking at how many inflammatory substances like hydrogen peroxide were actually in a wound, I couldn't find good data on what order that would be. So the 1 millimolar is a physiological concentration typical in serum. So of course 1 molar is totally out of the park. That's way larger. That's like straight hydrogen peroxide you get off the shelf. But we just wanted to see if they actually embrittled. So I wish there were better data as to how much inflammatory and reactive oxygen species there were, say, in wounds, but I couldn't find that. So we just did orders of 10 to see what would be significant.
Thank you. Any other questions from the audience? Oh.
I have one other question too. Why did you choose a cool environment, which is not physiologic?
Oh, by cool I just mean dark and not hot, because temperature can actually degrade plastic. So if these were kept someplace very, very hot, like we're from New Mexico outside in the desert, that can actually cause the material to change properties.
Good. Okay. Any other questions?